All right, so number 8, we have two functions. Let f of x equal 4 plus x and g of x equal square root of 2x. What is g of f of x? So this is what we call a composition function. We figure out what this is by taking our f of x function and substituting it into our g function. This is not multiplication, is not the g function multiplied by the f function. We do need to notice that the f function is on the inside of the g function. So to find this composition, what we do is we find our f function, which is 4 plus x, and we're going to substitute this into the variable of our g function. So we look at our g function, it's the square root of 2 times x, and this 4 plus x is going to substitute in for that x. So when we rewrite this, we have the square root of 2 times, instead of x, we substitute in our f function, which is 4 plus x. And then we just simplify this. We can go ahead and distribute that 2. So we have the square root of 8 plus 2x. And that is as far as that will simplify. So that will be our final answer on this one. All right, number 9, we're going to solve this equation. This is when we worked on radical equations. So here's our radical, we have a square root. Our first thing we're going to work on doing is undoing this radical so we can get to that x, get x's to the same side of our equation so we can solve. Now, to undo a square root, we're going to raise this to the power of whatever root we're taking. So a square root is a second root, so we're going to raise this to the second power. If we're going to do that on the right side of our equation, we need to be sure to do that on the left side of our equation. Now on the right, a square and a square root essentially cancel each other out, leaving us with just the 4x plus 5. On the left, however, we are squaring a binomial. So that x plus 2 squared actually is x plus 2 times another x plus 2. We have to multiply this out. I can't just square the x and square the 2. You do not get the correct answer when you do that. That's the number one mistake students will make on a problem like this. So if you're squaring this whole side, squaring means to multiply by itself, so write it out and do the actual multiplication. You have x times x, which is x squared. X times 2 is a 2x, and then you have another 2 times x, which is another 2x, which gives us 4x. So I am just combining this in my head right now. And then 2 times 2 is plus 4. So, you can write out all those steps, but you guys have multiplied plenty of binomials like this. So just understand you got to multiply, actually you got to distribute the x, distribute the 2, combine like terms to get this. All right, so let's get these x's to the same side. I'm going to subtract 4x from both sides. 4x minus 4x is 0. And then over here we have another 4x minus 4x. So really our equation is x squared plus 4 equals 5. We only have one term with an x, just that x squared. So why don't we isolate that? We can subtract 4 from both sides. I'll continue my work over here. So we have x squared equals 5 minus 4 is 1. And now we square root both sides. The square root of x squared is x. When you square root both sides of an equation while solving for x, we get two answers for this. X could be a positive one or a negative one. So plus or minus 1. Now, when we solve radical equations, when we do this step right here of squaring both sides, it's very possible that we are introducing or getting a false solution, one of those extraneous solutions. So we do need to check and see if positive 1 and negative 1 actually are solutions to this original equation over here. So I'm going to go ahead and write the original equation up here. It was an x plus 2 equals the square root of 4x plus 5. And we have to check both of our answers. We got a positive 1 first. So let's see if x equals 1 works. I'm going to plug in a 1 for all the x's. So 1 plus 2 equals the square root of 4 times 1 plus 5. 1 plus 2 is 3. Square root of 4 times 1 is 4, plus 5 is 9. And the square root of 9 is 3, so we have 3 equals 3, so that one worked out. So x equals 1 is a solution. Now let's see if x equals negative 1 is a solution. We're just doing our check right now. So I'm going to plug a negative 1 in for all of the x's. So we have a negative 1 plus 2. We want to know, is that equal to the square root of 4 times negative 1 plus 5? Negative 1 plus 2 is 1, equals the square root of 4 times negative 1 is negative 4. Negative 4 plus 5 is 1. So we have 1 equals the square root of 1 is 1, and that one also worked out. So we do have two answers, positive and negative 1. They both worked out in our check. All right, number 10, let h of x equal square root of x plus 3 and k of x equal 4x minus 14. Find h of k of 5. So what makes this one different, it's another composition. What makes this one different from the first problem on this page is we actually have a value of x to plug in. So let's go to the inside and first figure out what is k of 5. So k of 5, we're going to take our k function and we're just going to plug in a 5 for the x's. So here's our function. Instead of 4 times x, we're going to plug in a 5. 4 times 5 minus 14. 4 times 5 is 20. 20 minus 14 is 6. So k of 5 is equal to 6. So if I come back to the composition, it was h of k of 5, but k of 5 is 6. So I'm just going to replace that with a 6. And now we're going to find h of 6. So that tells us to grab our h function and plug a 6 in for your variable. So our h function is the square root of x plus 3. So we're going to do the square root of, we're going to replace the x with a 6 plus 3, and then just simplify this. 6 plus 3 is 9, and the square root of 9 is 3. So our final answer of this composition is 3. All right, number 11, we have a word problem. It says in 2022, there were roughly 350 eastern box turtles found in Michigan. The population is increasing by 12% per year thanks to zoo breeding programs. Write an equation that represents the number of turtles in Michigan in X years, and then find the number of turtles that should be expected in the year 2030. All right, so first we're going to write a function. This is what we call an exponential growth function. We have something that is increasing, it's growing by a percent every year. So our exponential growth model, f of x equals a times 1 plus r raised to the x power. We're going to follow this. This a value out front, that is going to be our starting amount, in this case, our starting population. In 2022, we had 350 of these turtles. So f of x equals 350 times 1 plus, now that r is that percent that we're increasing by, so 12%, but we do have to turn this into a decimal. So instead of 12%, we're going to say 0.12 raised to the x power. All right, so our function, f of x equals 350. We're just simplifying. 1 plus 0.12 is 1.12 to the power of x. So there's the first thing we're looking for. It says, write an equation that represents the number of turtles in Michigan in X years. Now we're going to use this to find the number of turtles that should be expected in the year 2030. All right, so let's go ahead and use our function. Now, x is our number of years, and we're looking at the year 2030, but how many years is that? And then you might say, well, how many years since when? So because we're starting out with 350 turtles in 2022, we want to use our number of years. How many years since 2022? So 2030 is 8 years later. So we're going to figure out the population in 8 years, 8 years after that starting population. So we're going to figure out what f of 8 is. That just means take our function that we already figured out, 350 times 1.12 raised to the 8th power. And then we're just going to do this math. If you grab a calculator and type that in, you get 866, and it's about equal to, I'm doing some rounding here, 0.6, but we're not going to leave a decimal value just because we are talking about turtles. So we'll say it's about 866 turtles versus the 0.6, because I can't have 0.6 of a turtle. All right, moving on to topic 6. This is when we got into logarithms and all that fun stuff. It says, find the inverse function of f of x equals log of 8x. So first, let's start by rewriting this with, instead of f of x, we'll rewrite it as y equals log of 8x. So anytime that we have to find the inverse, our first step is we are going to switch our y and our x variables. So those switch, then we're working in the inverse, and we will go ahead and solve that equation for y. So let's switch our x and y first. So we're going to have x equals log of 8y. So when you guys find an inverse function, you do want to solve for your y variable. Now our y variable is kind of locked into this logarithm. So what we do to access this y is we're going to take this out of log form and put it into exponent form. So we look at our log and we ask ourselves, well, what base is our log? Because remember, we have a base raised to an exponent equals this 8y. So when they don't write the base in, you guys will remember that that's when there's a base of 10. So 10, and then your log is always equal to the exponent. So this is going to be 10 raised to the x power is equal to whatever we were taking the log of, 8y. Now that we're in exponent form, that y variable is no longer locked down in a logarithm, so we can solve for it. To get the y alone, we'll just divide both sides by 8, and then our inverse function will be y equals, now this is a 10 to the x power, it's not just a 10, so I can't simplify the 10 over the 8, so that will just stay as 10 to the x power over 8. Another way to write an inverse function, this was f of x. Here's our notation, f with that kind of looks like an exponent of -1 equals 10 to the x over 8. So that's the inverse function of x. So we could write it both of these ways. If you notice, the function itself is 10 to the x over 8. It's just a matter of our label out front. Both of those would be good. All right, number 13, solve for x. We have 5 to the x plus 2, 5 to the 5x plus 2 power equals 125 to the x minus 6. So in Algebra 2, this was the first time that you guys started solving for variables that were exponents. We hadn't done this before. One method we learned how to do this was to see if we could get a common base across our equation. The left side has a base of 5. Can we rewrite 125 as a base of 5? So we actually can. I'm going to carry down the left side. 5 to the 5x plus 2 power is equal to, now 125 is the same thing as 5 to the third. 5 times 5 times 5 is 125. So we're going to take that 125 in our equation and replace it with that 5 to the third. I'm going to carry down the x minus 6 exponent. So our goal is to get a common base. So we got our bases of 5s. I'm just going to clean up this equation a little bit. We have a power raised to a power over here, so we can use one of our exponent properties. But first I'm going to carry it on the left side, 5 to the 5x plus 2 power equals, now this 5 to the third power raised to the x minus 6 power. When you have a power to a power, you're going to multiply your exponents. This 3 is going to multiply to the x and the -6. So we're going to have 5 to the 3x minus 18 power. Okay, so this is looking good. We have an equation with a common base. So see how 5 to a power is equal to 5 to a power? So if your bases are the same, that means that our exponents are the same. So that's the equation that we are going to work with. We're going to take out that 5x plus 2 and set it equal to the 3x minus 18. Again, if your bases are equal to each other, that means the exponents must be equal. And that's what we're going to work with. So when we solve this equation, we're going to start by getting the x's to the same side. So let's subtract 3x from both sides. 3x minus 3x is 0. 5x minus 3x is 2x. Carry on the plus 2 equals, that is a negative 18. Let's subtract 2 from both sides. So 2x is equal to negative 20. And then last, we're going to divide by 2. We get x equal to negative 10.